Hi, this is Roger from Kainkai Labs, and today I'm going to show you two little tricks how you can either measure or calculate the output impedance of a circuit. Now, where does this come into play? Of course, when you have a voltage source, let's suppose you have a DC power supply, then you can assume the output impedance is nearly zero. It will be with a good power supply be in the milliohms range, and you don't have to care much about it. But if you have a signal or function generator, then you usually have output impedances of either 50 ohms if it's radio frequency and 600 ohms when it's about low frequency signals, for example for audio measurements. But you sometimes have unknown output impedances, and let's suppose it could be the output stage of an audio amplifier, but not the power output stage, but the line output. And you want to know, well, which output impedance does my line output of my audio preamplifier have? And you can suppose the output impedance will only deal with the resistive part and not do any complex calculation. So let's suppose we have an unknown output impedance R, which is in series with your output driver stage. And here you have the terminals that could be an RCA jack or whatever. And now how do you determine when you don't get inside and don't have the circuit diagram available, how do you measure what output impedance you have? Now there's one little trick to easily find it out by measuring. Suppose you have here your unknown output impedance, and now you put a load resistor to your output, and without any much calculation, if your test resistor, which represents the load, is the same as the output impedance, the unknown output impedance of your source, then the voltage at this point will get divided by 2. So you just take an AC millivolt meter or an oscilloscope, and you first measure the signal amplitude without any load, and then you take like a variable resistor like in this RLC-Box, or a steppable resistor like in the RLC-Box, which I've shown you already, where you just take the independent resistor output and you play around a little bit. Watch the display of your either multimeter or your oscilloscope, and find the point where the output impedance gets to 50% of its unloaded value, and then you know that your load resistor is exactly the same as your output impedance. So that's the way how to measure an unknown output impedance. And now let's take a look at a more fundamental way how to calculate it if you have the circuit diagram available. So just to verify our theory, I've made a little test setup. We have our function generator, which I've set to something around 200 Hertz, so not to get any high frequency effects. It has a nominal output impedance of 50 ohms, but we'll check now if this is really so. I've set the Rigol DS1054Z so that the amplitude is exactly 4 divisions a peak. And more accurate, we can see it on the multimeter, so it's nearly 501 millivolts. And here we have our variable resistor and capacitor box. I'm only using the 1K trim pot, the 10-turn trim pot, and at the moment I have not connected it, and it is set to the highest resistance of 1K. And now I'll connect it, and you see that already this 1K load slightly dropped the voltage, and now we'll try to find where we get on the oscilloscope to 2 divisions peak and more accurate on the multimeter to 200. Now we have already reached it, just gone a little bit too far. Let's turn it back. And nearly now we're at 250 millivolts and 2 divisions. Now, if we take a look at the scale here, we're nearly at 50 ohms, but the scale is not 100% exact. So to measure the exact resistance we got dialed in here, we'll disconnect the function generator. Let's pull it off. And now we go to resistance measurement, and we got 48 ohms. So the nominal output impedance of the function generator of 50 ohms is nearly exactly verified as being 48 ohms. That shows that we can, with this kind of measurement, just dialing in until the amplitude has dropped to 1/2 of its unloaded value, we can determine the output impedance of any source. But you should never do this with a power supply or with a power amplifier, because then there's the danger that the resistor you are using for making this check starts to heat up and even burn in the end. So you should be, of course, be aware about the output impedance you expect from your source. If it's a low impedance source like a power supply or power amplifier, you should try this out only with power resistors. But as in this case, for 50 ohm sources, there was no problem in measuring with a simple variable resistor box just to find out the output impedance of the function generator. So that was test number 1, and let's go now to the second possibility. First of all, let's take a look at the theory. So let's suppose we have the circuit diagram available, and let's suppose this is the point where the last output transistor or IC is situated, and let's suppose this is our voltage source, mostly AC, and now comes something like this. From the output stage there is a voltage divider, and your real output, which could be an RCA jack or anything like that, is situated here. For simplicity, let's presume we have these two resistors are equal and they are both 1 kilo ohms. So we have a voltage source, we have a 1K resistor divider, and we have here the voltage is, of course, let's call this V1. The voltage, of course, gets divided by a factor of 2 because it's a 1-to-1 divider. So the output voltage we measure is V1 divided by 2. So that's no problem. But now what's the output impedance of this circuit? And that was a trap as a boy I fell into. I always thought, well, it must be 1K, because however you see it, that's the resistance that comes from the output stage and goes into V1. Or you could look upon it as, well, that's the resistor that the output is shunted to. So I always thought in a divider stage like this, after the last power output stage, that the output impedance is either this resistor or this, and both, of course, is wrong. Otherwise there would be no cause for this little video. So let's think again what we had before. We know that if we here have an external load, that when the output voltage falls to 50% of its unloaded value, then the load that does this effect is exactly equal to the composite output impedance of any, however complex, circuitry that's here behind the output jack. So now think for yourself for a minute, which resistor would we need to halve the output voltage? So the surprising answer is we would not need 1K, but we would need 500 ohms. So why is that? Let's do the calculation. We already know without a load we get half of the source voltage here from the last output stage. Okay, now we are seeking a resistor Rx, which again halves us this voltage, so which then we would need a division ratio of this combined voltage divider of 1, 2, 3. Now, why is that? Again, think for a second. If the two parallel resistors here, this 1K and this unknown load resistor Rx, if they are exactly 1/3 of this 1K resistor, then the voltage will divide in a ratio of 1 to 4. So then we get 1 here on the loaded output. We get the 1/4 of the original voltage, and that was exactly what we are seeking. So when does a combination of two resistors, one of which is 1K, the other one is unknown, when does this give a ratio of 1 to 3? So the answer is if the combination of these two parallel resistors give a resistance of 333.3 ohms, then we have the ratio of 1 to 3 between these two parallel resistors and this one. And how do we get to know now what this what's the value of this unknown resistor is to give us in parallel with 1 kilo ohms 333 ohms? Now use the formula for parallel resistors and you'll find it's 500 ohms. So we now know from experiment that obviously what I thought as a boy, that the output impedance of such a voltage divider circuit fed by an ideal voltage source, that it's 1K, but that's wrong. It's 500 ohms. Now, there must be some error in thinking, or there must be a reason why there's such a difference between what I thought from intuition and what's really true. And let's take a new sheet of paper to find out the fundamental reason for that. So I've redrawn the circuit in a general way. Again, we have an ideal voltage source, which represents the last stage of the output stage of whatever circuit we have. And then before we get to the output jack, we have a voltage divider consisting of two resistors, R1 and R2. Now let's think for a minute what this means. We have one resistor which shunts the output down to ground, that is R2. But what is the effect of R1? Now, when you realize that an ideal voltage source has an internal resistance of 0, then you see that here we also have a connection to ground. And we can look upon this as very simple. It looks in the end like this. We have R2, which shunts the output fed from R1 to ground, and we have R1, which also shunts the output to ground. Now we leave out the voltage itself, but we have to know that an ideal voltage source has an internal resistance of 0, and that is a path down to ground. And now everything becomes clear. The output impedance is simply R1 parallel to R2. And now let's take a look again at our simple example with two equal resistors of 1K in our voltage divider. Now we found out from measurement that we need that the output impedance is 500 ohms. And now everything falls into its right place. If two equal resistors of 1K are paralleled, we get 500 ohms. And that's exactly what we found from our fundamental thinking. I've just chosen two equal resistors just for leading you a bit on the wrong track and but nevertheless making the calculation simple. That is something you always have to remember if you didn't know it beforehand. It took me, well, many years before I found out the reason. It's very simple. Once it makes click in your mind, the output impedance of a voltage divider that is fed by an ideal voltage source, no matter if it's DC or AC or whatever, is simply the result of the paralleled resistors R1 and R2. So just to check if reality meets theory, I've made again a little test setup. We have here a resistor divider consisting of a 2K and a 1K resistor. That means at the connecting point we should get 1/3 of the voltage that we feed in. Why is that? Because the total resistance is 3K and the lower resistor is 1K, which means here we should get 1K divided by 3K, 1/3 of the voltage we feed in. And I've tried to dial in as good as possible 10 volts. So our multimeter is here connected to the connecting point of the two resistors, and we get 1/3 of 10 volts, which is exactly 3.33 volts. The variable resistor box is not connected at the moment. As you can see, only the lower end is connected, the middle point is not connected. Now let's first calculate with our trustworthy Casio FX61F what the paralleling of a 2K resistor and a 1K resistor should give. It should give 666.66 ohms. And now let's see what happens when we connect our variable resistor box. We have to find the point where the voltage again drops to 1/2, which would be 1.666 volts. And I've set it as a starting point to its maximum value of 1K. We see, after waiting a little bit for acquiring the measurement value, it already drops to 2 volt, and now we turn back the resistance until we get 1.666 volts. And because of the long integrating period, I'll have to do this quite slowly, but we're coming nearer and nearer to 1.666 volts. Now we're nearly there. And okay, that should be it. I'm sorry that the dial here is not in focus because I don't have enough light that all is in focus here. Let's adjust it now. That shall be good enough. If we read the dial, we get 660 ohms, and now let's measure the true resistance by disconnecting the power and going to ohms measurement, and again disconnecting these two connections so that we only measure the resistor box. And we get 0.663 kilo ohm, which is 663 ohms. So that's near enough to the theory. The inaccuracy is of course due to I cannot 100% exactly set the values. So it's exactly what we expected. The output impedance of this resistor divider consisting of 2K and 1K is exactly the value of the two resistors in parallel, which should be 666.66. And we're getting near enough. The remaining difference are simply the tolerances of the resistors and the test setup, etc. But you could see again, with this method we can again measure the true output impedance of any voltage source. However, the internal wiring, if there's a divider or only a single resistor or whatever, we can measure this quite accurately, and it's a nice and quick way to determine the output impedance of an output of a signal source. So that was it for today. I hope you liked it, and see you next time. Bye from Kanka Labs. Bye from Roger.